Okay, in this video, we're going to be doing Calc BC Problem Set number 33. The problems and a playlist are in the description below. Let's take a look. This entire problem set is calculator, but instead of like editing in the videos of me using the calculator, which kind of takes forever, I'm just doing screenshots. If you're not sure how to do something, look back through the other problem sets. If I remember, I'll try to link some below. I've done everything in here in some problem set. So let's take a look. Let r of theta equal 5 root theta cosine of theta cubed, and S be the region bounded by r of theta on 0 to k, where k is the first positive value of theta for which r of theta equals 0. The region is shown above, but I moved it. So we need to find the area of S, which means we really need to find k. I mean, that's going to be important to the entire thing. So I need to figure out when r of theta is equal to 0. I chose to do that by graphing r of x in function mode on the calculator. Here's a look at what that looked like. And from that, we can see that the theta value where this happens is at 1.16245. I went as many as I could, and we're supposed to call that k. On the calculator, I'm pretty sure I stored that as a. It doesn't really matter as long as we're getting it down correctly on paper. So area is going to be 1/2 the integral from where you start to where you stop of r squared d theta. So that's really important. The 1/2 in particular, people forget. But polar area is not the same as rectangular area. You're not just doing rectangular rectangles. You're using quote-unquote polar rectangles. But anyway, here's a screenshot of that, and I got approximately 5.191. So let's jot that down. That's our answer. Let's take a look at the next part. So find the average distance from the origin to the points on the curve r of theta on 0 to k. If you get k wrong, you're basically in trouble on this one. What'll happen though when you get something like that wrong, in theory, they will read with you. So like if you got that theta was 2 for some reason, as long as you keep using 2, you're still eligible for like setup points, possibly for answer points using your own wrong thing. It just depends on how much effort they're putting into grading, and like, how far off track you are. But anyway, we're using this value of k. We're looking for the average distance. R is the distance from the origin to a point on the curve. So I'm just going to do average value of r. So that's going to be the integral divided by the interval. So it's from 0 to k of r of theta d theta divided by k minus 0. So integral divided by interval. We did the math on that. And I got approximately 2.803. I mean, if I did it right, I flashed a picture up there of the calculator screen, hopefully. All right, let's take a look at the next part. Find the slope of the line tangent to r of theta at the value of theta for which r of theta is a maximum on 0 to k. All right, so this one's a little more complicated. We have to figure out the maximum. You can see in the picture that there's definitely just like one critical point, and that's going to be where we're at a maximum. We need to figure out where r prime is equal to 0. So we need r prime to equal to 0. I'm going to use a calculator for that. I'm going to graph r prime of x in function mode, and find the intersection point with the x-axis. So that's what I've done there. We figure out that in this case, the theta that we're getting is 0.735113. And I named that b because in the previous parts, I have accidentally called the value of k a. So I went with b. All right, now, to find slope in polar, it's still dy dx. We need to convert from polar to rectangular. Really, we're converting like polar to parametric in my mind. But we're going to use the equations. X is r cosine and y is r sine. I think it's important that you write that so the person grading it knows where you're getting anything from. And then dy dx. This is a calculator problem, so we don't have to like do anything by hand. But dy dx at t equals b is just going to be y prime of b over x prime of b. So here's a screenshot of what I did. I defined x, I defined y. I put a 1 with all of them because I don't like to define things as just x. That's more writing though. So if you choose to do it, just do it, right? And then I found the derivative. So I got that the value here is negative 1.106, and that's the entire problem. All right, let's take a look at the next one, number 2. Let r be the region shown above or to the side, bounded by f of x, which is cosine of x over 2 plus 2.9, and g of x, which is negative 0.25 natural log of x plus 3 plus 2.8. We want to find the area of r. All right, so for this one, We need to figure out where they intersect. So that's going to be when f of x equals g of x. Then we need to like set the whole thing up. I'm going to put up a screenshot here of what I did. The calculator gets these values. We don't have to watch that. The calculator finds the intersection points for us. And then what I did was I used bounded area, because bounded area is going to get you the correct answer, even though I'm skeptical of it. You can see in the picture, once you've used your calculator to graph them, f of x is the top curve and g of x is the bottom curve. So when you're doing area with respect to x, it's always top take away bottom. So our integral will be the integral from a to b, top take away bottom, f of x minus g of x, and we got 6.297. All right, let's take a look at the next one. We want to find the volume of the solid formed when the region R is rotated about the line y equals 4. So these are the intersection points again. Let's just import those. Here's y equals 4. So y equals 4 is above the region, which is important because we have to figure out like our big radius and our little radius that we're going to rotate. So big radius, you go from the axis to the outermost curve, which I'm going to call R1 in this case because R is already the name of the region, so you don't want to use just capital R. That would be a little confusing. You can see that 4 is on top, so this is going to be 4 minus, in this case, g of x is farther. That's the natural log curve. So 4 minus g of x is the big radius, and then we need the small radius, which is, the inner curve to the axis. So that's going to be 4 minus f of x. The functions are named, so at no point in time will I be writing those functions by hand. I'm not going to write cosine of x over 2 plus 2.9. That's crazy. I'm just going to use the name of the function, f and g. All right, so volume is going to be pi. Don't forget pi. The integral from a to b, and then it's big R squared. So that's 4 minus g of x, quantity squared, and then minus, we're just doing big volume minus little volume, so minus little r squared. So quantity 4 minus f of x squared, and then the whole thing is dx. All right, and so then here's a calculator page where I just did it. I got 37.248, I guess, when you round it, and that's all there is to it. So let's take a look at part C. Region R is the base of a solid whose cross sections perpendicular to the x-axis are semicircles with diameters in R. Find the volume of the solid. All right, so semicircles, we know we're just going to integrate pi over 8, the integral from a to b of s squared, and then dx. We just have to figure out what s is, because the intersection points, again, they're carrying forward. So s is going to be the distance from the top to the bottom, which is top takeaway bottom. I call that s for segment. So the segment that we're utilizing in our formula is going to be top takeaway bottom, which is f of x minus g of x. We still need those intersection points, so I'm just going to pop them in there again. They're still stored as a and b. So we got to set this thing up, right? So volume, when you're dealing with semicircles, pi over 8, always pi over 8. So memorize that one in particular. Semicircles, equilateral triangles, super important. Otherwise, it'll probably be described to you in a way that you can just work out the geometry of the situation. I also think that isosceles right triangles are useful to know. But, these are the things that we really need to know. Semicircles, equilateral triangles, rectangles, squares. Those are the only ones I think are in the actual course description. So we got pi over 8, integral from a to b. And then it's s squared. But I'm not going to write s squared because I don't like to mix variables. So s is f of x minus g of x, so it's quantity f of x minus g of x, and then squared. So that's s, and then squared, dx. Okay, so here's the calculator page. Pretty straightforward. You can see we got approximately 2.694. So let's write that down. And there you go. That's the entire problem set. I hope this was helpful, and good luck.